How's it going, everyone? Cup of Science Joe here. Now, most of us are familiar with visual astronomy, and while it can teach us many things, it does not tell the whole story. The universe radiates at wavelengths that are not visible to us as well, and within these hidden wavelengths, there is so much more we can learn. One such example of this is radio waves. These are the longest of the wavelengths that are part of the electromagnetic spectrum and can range from the length of a football to even longer than our planet. They sit in the 30 kilohertz to 3 gigahertz section of said electromagnetic spectrum. Now, you might be familiar with radio waves. Have you ever used a radio to tune into your favorite music station? That music was being broadcast to you using radio waves and picked up by your stereo's receiver. But did you also know that astronomical objects can emit radio waves too? Like with our music, we can detect these waves to learn things about the object emitting them. This has resulted in the field of radio astronomy. We did not always think to use radio waves for studying the universe, though. It was not until around 1932 when Carl G. Jansky was faced with a problem. Noisy static was interfering with the shortwave radio transatlantic voice communications. You see, Carl was an engineer for Bell Laboratories at the time, and he was tasked with finding a way to prevent this. After months of tracking what ended up being 3 different sources, he made an interesting discovery about one of them. One of the sources of interference was shifting slowly across the sky, and it almost seemed to not be coming from our solar system. Stumped on this, he sought the help of astronomers, which resulted in the writing of radio waves from outside the solar system, a paper that would lay the groundwork for radio astronomy. But what exactly was it that he had detected? Well, more on that one later. While Carl did not pursue this area of study further, work and research did not end there. Only a handful of years later, in 1937, an engineer by the name of Grote Reber built the first dish antenna radio telescope. He achieved this using rafters, galvanized sheet metal, and spare parts from a Ford Model T. Truly impressive. With this 31-foot diameter telescope, Reber would map the radio structure of our galaxy, discovering bright sources of radio waves from outside it. He would also make discoveries that would later aid physicists in discovering non-thermal radiation. Now let's move forward in time, about another 30 years or so, to the year 1967. Radio astronomy by this time was more established, and we're going to turn our attention to a young graduate student named Jocelyn Bell. Jocelyn would make an important discovery using radio astronomy. Bell had helped construct a radio telescope, and while reviewing data from it, she noticed a strange signal on the printout. At first, she was not certain what this signal was, but it was created by an object emitting radio pulses about 30 times a second. This object was nicknamed LGM1 because they joked that it could be caused by little green men, but it actually turned out to be the discovery of the first pulsar. Speaking of discoveries, what exactly was it that Carl had discovered back in 1932? Well, it turns out that the source of those radio waves was none other than Sagittarius A, the supermassive black hole that resides at the center of our galaxy. So there we go. In the pocket of radio astronomy, we have the initial discovery of Sagittarius A and the first pulsar. Let's now talk a little bit about radio telescopes themselves. Modern radio telescopes are basically a giant dish pointed at the sky. But because radio waves are so big compared to other types in the electromagnetic spectrum, radio telescopes must be physically larger than optical telescopes if one wants to make images of a comparable resolution. Let's have an example. The Parkes radio telescope, seen here, has a 64-meter wide dish, yet it is unable to yield an image any clearer than a small backyard optical telescope. Now you might wonder, all of that data contained in those radio waves is super juicy, and we know scientists and I want more of it. So how do we collect something in high resolution when the required dish size would simply be too large? The answer to that lies in numbers. In order to make a clearer, higher resolution image, radio astronomers will often combine many smaller telescopes into an array capable of receiving very large signals. One such wonderfully named example of this is the VLA, also known as the Very Large Array. The VLA consists of 27 antennas that are arranged in a big Y-shaped pattern that is up to 36 kilometers across. Now that is a big receiving area. And this additional receiving area allows us to come up with images like these. With evolving technology, the use of radio astronomy still continues to develop to this day. And it serves as an important tool for us to broaden our understanding of the universe and reveal details to us that may have otherwise remained unseen and undiscovered. I hope you've learned something, and I implore you to step outside tonight and look towards the stars.